We will start in 5 minutes. Hello and welcome to week 4 of the live problem solving session for the NPTEL course Introduction to Semiconductor Devices, which is being taught by Professor Naresh Kumar Imani from IIT Hyderabad. The course ID is NOC 25EE92. So, I am Mayank Goel. I am a research scholar at the Department of Electrical Engineering at IIT Bombay. The details about this course. So, this course is being taught by Professor Naresh Kumar Imani, who is an associate professor in the Department of Electrical Engineering at IIT Hyderabad. So the course plan for this week is PN junction electrostatics, fixed and free charges, depletion approximation, electric field at the junction, built-in potential, step junction versus linearly graded junction, energy band diagram of a PN junction, and quasi Fermi levels. So this live problem solving session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So first we will do a recap of the lecture using the notes provided by Professor Arish. So this week we will start with PN junction. So a PN junction is basically when you join, you take an p-doped semiconductor and an n-doped semiconductor and you fuse them. So that is called a PN junction. So the point where they meet is called PN junction. So first it's so first we talk about step graded PN junction, where or also called abrupt PN junction. And let me start here. So this is a PN junction where you have a p-type material and an n-type material, and they are joined together. And the quality of this junction is very critical. So how PN junction is made? Generally, it is you take a p-type substrate and you deposit n-type dopants in it, so that you get a NP junction, PN junction. So for that you can do photolithography and then bombard phosphorus or arsenic ions, which are n-type ions, and they will diffuse they will diffuse or ion implant here and make this region n-type while the rest of the region is p-type. So that is how generally a PN junction is made in industry. Yeah. So the first, the n-type doping is to overcome this p-type doping, and then you do extra doping to make it n-type, which is what is shown here. So in an IC, it's a PN junction looks like this. So you have an n-type wafer. So first you make a p well in it, which houses your device. Then in that p well, you make an n plus doping area. So this becomes your PN junction, and then you make contacts on this n type area and this p type area. So these are our two contacts for our PN junction. And SiO2 is used to block this from outside, except where you need contacts. So this fabrication you will study in detail in later classes. So there are different types of PN junctions. First is abrupt junction, where where your your left side, your P area is uniformly P type, and your N area is uniformly N type with same dopant density. So you can see it's for x greater than 0 it's Nd, and for x less than 0 it's Na. Then there's linearly graded junction, where near the junction region your density is not constant in P type and N type region, but it changes linearly from P type to N type. So your Nd minus Na in the junction near the junction region is proportional to x. Then you have P plus N junction, where one sided is heavily doped and the other sided is lightly doped. Similarly, you can have Pn plus junction. So P plus N junction means the P doping is very high, whereas N doping is light. Pn plus junction, where N doping is high and the P doping is low. So So let's an example of P plus N junction would be where ND is 10 per 15 and N is 10 per 20. So there's a huge difference between the doping. Next is PIN junction, where between a P and N you insert an intrinsic region to for slow change in the PN. From P to N, you insert an intrinsic region, small intrinsic region in between the P and N regions. So now, when you form a PN junction, what happens is due to difference in their concentration, holes. So this region has a high density of holes and a low density of electrons, and this region has a high density of electrons and a low density of holes. So holes will diffuse from this region to this region, and electrons will diffuse from this region to this region. And what will happen is, due to this diffusion, they will there will be an excess of holes near the junction on the right of the junction, and an excess of electrons in the left side of the junction, and this will create an electric field, and a negative electric field, and this electric field will then stop further movement of holes and electrons. It will oppose the further movement of holes and electrons, and so these excess holes and excess electrons become fixed in this region near the junction, and this region is called your depletion region, because due to this excess charges, the charges majority carriers are excess minority carriers here, the majority carriers are depleted in this region. So away from the depletion region, your Na and Nd, they are the same, so they are called quasi neutral. There is no charge buildup in these regions. Only the charge buildup is in the depletion region. So these are called fixed charges, and these deplete the free majority carriers, which are which is why this is called depletion region. So the electric field that is formed at opposite diffusion, and hence an equilibrium is achieved. So you can see initially this side holes still here, and this has electrons still here, but the holes from here have moved here and the electrons from here have moved here. So that has caused depletion in this region of free charges. So hence you have holes still here. Then in the depletion region, so the depletion region is denoted as, so the junction is called x equal to 0. The left side is p type, right side is n type. So depletion region width is minus xp here on the left side and xn on the right side, on the n side. So you can see beyond the depletion region we have full density of holes and electrons, holes in p type and electrons in n type. But in the depletion region there is no holes and electrons, majority carriers, they are fixed. Whereas the fixed charges, they are only in the depletion region and not outside the depletion region. So in the P type depletion, in the depletion region, the P type semiconductor, there are negative charges, and the depletion on the right side, on the N type region, there are positive charges. So for an abrupt junction, this charges in depletion region will be constant. and which means there are the doping here is if the doping is uniform, this will be constant charges. You can see here it's known as QND here and QNA on the left. So the electrostatic equation is given as Laplace square V equals to minus rho by epsilon naught, where rho is the charges in this region, which means dE by dx equals to rho by epsilon Si. So the charges are calculated by the derivative of the electric field, or you can calculate the electric field by integrating the charges in this depletion region. So you can see from 0 to x to xn, the electric field dE by dx is equal to q nd by epsilon Sa, because your rho is q nd. So if you calculate, epsilon is q nd by epsilon Sa x plus c. And similarly for here, your electric field will be q na by epsilon Si x minus q na by epsilon Si x plus c. So it will go like this and it will go like this. So this is how your electric field will look like. It won't look like this because in this region your first electric field goes negative and then it goes positive, but it's starting from a negative value, so it remains in the negative region. So hence in this whole depletion region, your electric field remains negative, which means it's pointing towards your it's pointing to the left for this whole depletion region. This is the calculations. You can do that. You will get the equation electric field equals to minus q nd epsilon sa xn minus x and minus q na by epsilon sa x plus xp. So that you put here, you will get electric field like this, and you will see that the electric field is continuous at x equals to 0. So you cannot have a discontinuous electric field for this type of junction. And if you use the continuous boundary condition, you will get ndxn equals to naxp. So which means the charges are balanced across the junction. So the depletion the dep, so you multiply the depletion with the number of charges in the region, and that will come out to be the same as the other region. So which means the charges here is equal to the charges here. So you multiply. So this is naxp and this is ndxn. So the area of this equals to area of this. So that means the total number of charges are in this region is equal to the total number of charges in this region. Hence, which should be the case for charge neutrality. And this, so you can see that at this point, the electric field is maximum at the junction point and minimum at the end of depletion regions. So this maximum electric field E naught will be minus q na xp by epsilon si or minus q nd xn by epsilon si. Also, electric field is minus dv by dx. So you can calculate v by integrating over the electric field minus integration e dx. So which is basically area under the electric field. So this area gives you the voltage. So if you integrate over this region, you will get the voltage to go from 0 to some value here, and this increase in voltage is called a VBI or built-in voltage. So you integrate over the formulas that we had studied in for the electric field. These formulas you integrate over them, you will get VBI equals to half Xn plus Xp the Q Na by epsilon Si Xp, or you can also write it as Q by 2 epsilon Si Nd Xn square plus Na Xp square. So how the energy bands look like in a PN junction? So you have a p-type region where the Fermi level is near the valence band, and an n-type region where the Fermi level is near the conduction band. So when the two come closer, the Fermi level has to align. So so bands of one of the regions shift with comparison to the other region to to equate the Fermi level, and hence you have a curvature in the band near the junction, and this change in the energy is called your EVBI, or the built-in energy of the built-in potential. And you can see the away from the junction, your individual band diagrams looks similar to earlier, with the same phi FP and phi FN gaps as earlier. So question: calculate the built-in potential barrier in a PN junction. Consider a silicon PN junction at T equals to 300 K with doping concentrations of Na equals to 2 into 10 per 17 per centimeters cube and Nd equals to 10 per 15 per centimeter cube. So, so till now we have studied this formula NaXp equals to NdXn, and the electric field is given maximum electric field E naught is given as minus q Na epsilon xi xp equals to minus q nd xn by epsilon si, and the built-in potential is q by 2 epsilon si nd xn square plus Na xp square. So the charge is given like this, where this is so this is for an these are all for an abrupt junction. Charge here is qnd and qna, and you dif, you integrate over this, you get your electric field like this. You integrate over your electric field, you get your voltage, which looks like this. The potential looks like this, and this change in potential is called your VBI. And so you have your energy bands like in p type like this, n type like this. So when they join, your Fermi level has in equilibrium condition, the Fermi level is constant. Hence these bands shift downwards to make the Fermi level same, and hence you see this dip in the bands, and this change in the bands from this to this is your built-in potential. So the steps is drawing a band diagram. So first you draw the Fermi level at equilibrium, because the Fermi level is constant. Then you draw your EC and EV in quasi-neutral regions with the so quasi-neutral regions are the regions that are far from the Fermi level, far from the junction, from the depletion region. So this region and this region. So so here your Fermi level is like this. And so you draw the rest of the bands accordingly. this, and this. Similarly, here your Fermi level is like this. So rest of the bands you draw this, and this, and then you just join these bands in the depletion region while keeping the band gaps constant. So you can see in the quasi-neutral region, the bands are constant, so electric field is zero. There, there is no bands are constant in the quasi-neutral region, so electric field will be zero in the quasi-neutral region. In the middle region, the bands are going down, hence the electric field is negative in these regions. So you have so this is an n-type region, so you will have an excess of electrons in the conduction band, and this is a p-type material, so you have an excess of holes in the valence band. So if the electrons want to move from here to here, they cannot move due to this huge barrier. Similarly, holes cannot move from here to here due to this huge barrier, which is your, in both cases this barrier height is the same as your built-in potential. So in both cases, they are seeing a potential barrier equals to VBI. So to so they will have to gain an energy equal to VBI to overcome this barrier and move for electrons to move from here to here and the holes from move from here to here. So unless you provide this energy, there will be no movement of electrons and holes from one region to the other region. Next is depletion approximation. So you take this central region as your depletion region. So when you draw these, so you will see there is some curvature to it, but we have all assumed that there are no free carriers in depletion region. So what we will do is we won't consider this curvature. We'll consider these as straight lines. So ideally your depletion region looks like this, but we will consider them to be like this. So your so your ideal equation for your charges is given as Q P of x minus Na minus Nx plus Nd, Na minus and Nd plus. So the depletion approximation states that the depletion region is free of moving free of majority carriers or free of majority electrons and holes. So this Na minus and Nd plus will be the same as Na, and Nd. So that will allow us to calculate the built-in potential. So the built-in potential is given as the EC in the P region minus EC in the N region. In the P region, you can calculate your, instead of EC, you can write EI in the P region minus uh, EI in the N region, and that you can write in terms of Fermi energy as Fermi energy minus phi Fp and Fermi energy plus phi Fp and Fermi energy minus phi Fn, and you know how to calculate phi Fp and phi Fn, which is kT ln Na by Ni and kT ln Nd by Ni. So you add and the Fermi, so you cut that and you use the phi Fp and phi Fn, and that gives your VBI equals to phi Fp plus phi Fn, which is kT by Q ln Na Nd by Ni square. So if Na is 10 per 15 and Nd is 10 per 16, so when we talk about Na and Nd, we are talking about the individual doping in the region. You will see that Na and Nd are not equals to Ni square, and that is because when we talk about Na, we are talking about the doping in the N type region. When we talk about Nd, we are talking about the doping in the P type region. So they are not in the same regions. Hence, they're not equal to Ni square. So here the Nd will be 10 per 5 and here the Na would be 10 per 4. But we are only talking about the majority doping, majority carriers, which is Na is your N type majority carriers 10 per 15 and Nd is your P type majority P region majority carriers which is 10 per 16. So if we calculate the built-in potential at room temperature would be Kt by Q would be 60 millivolts. So you convert Ln to log and you multiply with Kt by Q, it becomes 60 millivolts. So it will be 60 millivolts into log 10 power 31, 15 plus 16, 31, and by n square 20. So this is log 11. So you log 10 power 11, so you multiply that will be 60 millivolt into 11. So it become 0.66 volts. So the built-in potential is less than your band gap. So for silicon, the band gap is 1.1 volts, 1.1 EV, and for gallium arsenide, it's 1.42 EV. So it's your built-in potential is generally less than your band gap, and the doping is generally less than 10 per 20 because at 10 per 20 your non-degenerate approximation breaks down. Hence, we generally keep the doping less than 10 per 20. So this question that we had now seen, we can now solve this question using the formula we just studied here. VBI equals to 60 milliwatt into log NAND by NA square. So you put that your NA is 2 into 10 per 17, ND is 10 per 15, and your NI you have taken as 1.5 into 10 per 10 here. So that becomes 2.25 into 10 per 10. So you solve it, you get approximately this value approximately gives you 12. So this becomes around 0.72 volts. So now if you so we know XPNA equals to XNND, and so the total depletion width from minus XP to XN is called W. So XP plus XN equals to W. So you put that here. XPNA equals to W minus XPND. So XP equals to NA upon NA plus NDW by solving this. And similarly, your XN will then be NA upon NA plus NDW. So from NA, ND, and W, you can get your XP and XN. Now consider now if we consider that ND is greater than NA, so if ND is greater than NA, then this will be NA plus ND is approximately ND. So ND and ND cancel out. So XP will be approximately equal to W. So we can say that XP is approximately equal to W if ND greater than NA. The doping here is much larger than the doping here. So the electric field in the center is we know it's minus q Na by epsilon Si xp. So xp we can write it as uh, as this. So it becomes minus q by epsilon Si x Na Nd by Na plus Ndw. So the built-in potential is approximately given as half W into peak electric field, which is half q by epsilon SA Na Nd upon Na plus Ndw square. So your W can then be calculated from a built-in potential as square root of 2 epsilon Si by q Na plus Nd upon Na Nd into Vbi. So from built-in potential and your dope, individual doping, you can get your W, and from W then you can get your XP and XN. So next question, calculate the space charge width and electric field in a PN junction for zero bias. Consider a silicon PN junction at T equals to 300K with doping concentration Na 10 per 16 and Nd 10 per 15. So first you calculate your VBI from this equation, and that comes out to approximately 0.66 volts. And then you use that to calculate your W. So epsilon Si you can use 11.7, and epsilon naught is 8.85 into 10 power 14 farad per centimeter. So it's important to use epsilon naught, your permittivity of free space, in terms of farad per centimeter, because your Na and D are in terms of centimeter. So if you use in terms of centimeter, you will have the equations cancelling out. Otherwise, if you use instead farad per meter, then you will have wrong. The numbers you will be getting will be wrong. So always, so in in semiconductors, in semiconductor physics, we generally use all terms in all equations in terms of centimeters. All units we take in terms of centimeters, not in meters or nanometers or something. Generally, we take all equations in terms of centimeters for ease of use. So you calculate W, put 2 into 11.7 into 8.5 into 10 per 14. Charge is your 1.6 into 10 to the power 19. Your Na plus Nd upon 10 power 15 plus 10 power 16 by 10 power 31 into 0.66. This comes approximately your 0.95 microns. So typically your W will come in on the range of 1 to 10 microns. Here it's coming out to 0.95 microns, which is approximately 1 micron. From here, then you can calculate your Xn and Xp, which come, so your Xn comes out to be around 0.85 micron, or Xp comes out to be around 0.085 micron. So you can see even one order difference creates such a huge difference between Xp and Xn. And then the peak electric field is Q Na by epsilon Sa Xp, which comes out to be around 10 power 4 volt per centimeter. So one-sided junction is the junction where your one region has a very high doping density compared to the other region. So the whole depletion region, as we have seen earlier, the whole depletion region is approximately in your lightly doped region, and in your highly doped region, the depletion region is almost negligible. So this is called a one-sided junction. So these equations we have just studied. So one-sided junction. So when you have ND greater than Na, that is a PN plus junction. Your XP is almost equal to your W. So your depletion region lies almost entirely in the P-type region. And for Na greater than ND, your Xn equals to W. And the depletion region will lie almost entirely in the N-type region. That is called a. Next is your. So till now we were studying abrupt junctions. Now we will study linearly graded junctions. So in linearly graded junctions, instead of having a constant charges in the p type and the n type region, you have a linearly graded charge region, depletion charge region. So your minus xp, you have a huge charge at your edge of depletion region, and as you go closer to your junction, the trap charge decreases, and then its trapped electrons decreases, and as you move into your n-type region, your density of trapped holes, number of trapped holes start increasing at our maximum at your edge of the depletion region. So in this case, for symmetric, we say xn equal. So for this case, xn equals to xp equals to w by 2. So your depletion width will be equally distributed in the both for charge neutrality, for maintaining charge neutrality. So in this case, your electric field, so your rho is then given as qmx, where m is the slope of this gradient. Mx is your slope of this linear grading. So you integrate over this, you electric field you will get as qm x square by 2 epsilon si plus c. So you can see that electric field in a linearly graded junction is quadratic. And so it was linear in for abrupt junction, but for linearly graded junction, the electric field is quadratic. And if you put x equals to 0, your electric field is 0. So you are the electric field is 0 at the edge of the junctions. So your electric field will be 0 at the edge of at minus xp and at xn. So which is at x equals to minus w by 2 and x equals to w by 2, the electric field will be 0. So you put that here. So from that you can calculate the C. So your electric field then comes out as qm by 2 epsilon si x square minus w by 2 square. So that you can then plot, and it comes out like this. So from minus w by 2 it goes like this to till w by 2, and this value is given by your m. So minus qm by epsilon. So you plot this, it looks like this, and then you integrate over it to get your v voltage potential equals to minus integration of epsilon dx. So we assume that at the start of the depletion region, your potential is 0, and at the end of the depletion region, your potential is equal to VBI. So using that assumption, we put here. So we integrate over this, we get qm by 2 epsilon si x cube by 3 minus w by 2 square x plus c, and in this we will put this to get our v of x. So for an we had seen that for a abrupt junction, our depletion width was proportional to square root of VBI. For a linearly graded junction, the depletion width is proportional to cube root of VBI. Hmm. So in a PI, so a PIN junction, you insert an intrinsic region in the center. So you have a P region with so you have a P region with a depletion de- negative depletion region and an N region with a positive depletion region. And in the middle there's an intrinsic region without any dope. So it's an intrinsic, there are no dopants in this region. So at equilibrium there won't be any excess carriers in this region. So there is no excess free charges or excess fixed or space charges. So there is no depletion region in the intrinsic region. The depletion region lies only in the P doped and the N doped regions. So for charge neutrality, you have xp minus x naught equals n to n naught equals to xn minus x 0. So we are taking assumption here the fixed space charge, the p-type region, p-type depletion region is minus n naught, and then the n-type region it's 3 n naught, and your intrinsic is at minus x naught here and x naught here. So for charge neutrality equation, this will be the equation we will follow. Now, what will be the electric field in this intrinsic region? So we know the electric field is integration of the space charge. Since space charge is 0 here, the electric field will be constant in this region. So what about built-in potential? So we know that the the potential is integration of electric field. So if electric field is constant, so our potential will increase linearly in this region, and which would mean our built-in potential will depend on the length of this region, length of an intrinsic region, as our depletion regions will be same as before. Depletion region will depend on the same as our previous same as abrupt regions. So only the increase will be in the intrinsic region. So there will be a linear increase in potential in the intrinsic region. So that will your built-in potential will then depend on the length of the intrinsic region. So your electric field is constant, so it will look like this. From minus xp to minus x naught, it's decreasing. Then it's constant, and then from x naught to xn, it's increasing again. And you can then calculate it from the given equations. So next we have semiconductor with a fixed charge. So you have a constant semiconductor, constant doped, constantly doped semiconductor, and in the middle you have a sheet of fixed charges. So charges will look like this. So this sheet of fixed charges will cause a depletion region in near the sheet. So it will look like this: minus xp till x equals to 0, almost till x equals to 0, and from x equals to 0, almost till xp. And so in the middle, there's your sheet charge which you are given. So your sheet charge is taken as a delta function at x equal to 0. So by charge neutrality, you will have qp equals to minus 2 na q xp, and for using this, and from this, if you calculate your electric field, you will see that your electric field is positive for x less than 0 and negative x, positive for x greater than 0 and negative for x less than 0. So you have from minus q xp till some value, you have electric field, and then there's a jump in the electric field because of this delta charge region. So then from some positive value, it goes to xp, it goes to 0 at xp. So you see, in this case, the electric field is not continuous, and that is due to this fixed charge which breaks the continuity. And when you calculate the potential by integrating over this, you will have from minus xp it goes to some value, and then from that value it comes back to 0 at xp. So you see the net built-in potential for this region is 0. So now we will come here. So these are some quick review. So consider a step graded PN junction and thermal equilibrium where P side dopant density is Na and N side dopant density is Nd. Diffusion of charge carriers creates a depletion region which is formed across the junction with W, which is typically 1 to 10 microns. The depletion region on the P side is Xp and on the N side is Xn, and then W is given as Xp plus Xn. Due to the net space charge density, there is an electric field exists in the depletion region and its direction is from N to P. A maximum field Emax is created exactly at the junction. A potential difference, also known as a built-in potential, is formed across the region, that is VBI. So in equilibrium condition, the electric field is continuous at the junction, and we have due to charge neutrality, we have QNAXP equals to QNDXN. The maximum from this, the maximum electric field is calculated. Emax is minus q na by epsilon si xp equals to minus q nd by epsilon si xn, and the built-in potential is calculated as minus q by 2 epsilon si nd xn square plus na xp square, or k also you can also calculate it as kt by q ln na nd by ni square. The width can be calculated from vbi as square root of 2 epsilon si by q 1 by na plus 1 by nd, or you can multiply this, it will become na na nd upon na plus nd into vbi, and then the individually xp equals to nd upon na plus nd w and xn equals to na upon na plus nd w. So now this that was for abrupt junction. Now one-sided abrupt junction. Consider a step graded abrupt PN plus junction thermal equilibrium where the P side open density is Na and the N side open density is Nd, and with Nd greater than Na. The depletion width on the N side is so small such that uh, the depletion width almost equals to the XP. The depletion will cover almost in the lightly doped region, which is Na in this case. Similarly, for P plus N junction, Na is greater than Nd, and then W is equals to Xn. So the profile will be in an abrupt junction, your depletion will be proportional to square root of VBI, whereas in a linearly graded junction, your W depletion will be proportional to cube root of VBI. So how the profiles will, with depletion approximation, the profiles will look like for an abrupt PN junction. Your charge looks like this, and then you integrate over it to get an electric field. For linear PN junction, your charge looks like this. You integrate over it, you get electric field like this. For a PIN junction, your charge will look like this. And when you integrate over it for electric field will look like this. For an abrupt PN plus junction, your charge will be like this almost. And then similarly, your electric field will look like this. So now we will do some practice questions. First question. So before that, there is a question in the chat. What are neutral dopants? So basically, dopants are any atoms that are not part of the not part of intrinsically part of the lattice. So for a silicon lattice, only the pure silicon lattice, only silicon atoms will be there. For any other if you are entering any other atoms that are dopant atoms, so neutral dopants are the dopants which do not contribute any charge to the any excess charge to the lattice. So like if you are giving boron, it will take an electron. It is an acceptor dopant. It will take an electron from the silicon lattice and it will make the lattice p type. Similarly, if you add phosphorus, it will make the lattice n type by giving an extra electron. But let's say if you are adding carbon to the silicon lattice, so what carbon will do? It will do nothing to the lattice because carbon also has a vacancy of 4, similar to silicon. Carbon also has a valency of 4. Silicon also has a valency of 4. So the carbon will just take the place of silicon without contributing or accepting any atoms. So first question, according to the depletion approximation, what primarily constitutes the electric field in the depletion region? Free electrons and holes, neutral atoms, ionized dopant atoms, both free carriers and dopant atoms. So the answer to this is actually C, ionized dopant atoms, because as per depletion approximation, the depletion region does not have any free carriers. So the free carriers are absent in the depletion region. So the what is left, there only the ionized dopants are left. So the, the electric field will be due to this ionized dopant atoms. For question 2 and 3, consider an abrupt silicon PN plus junction with a doping profile as shown in the figure below. Based on the doping profile, answer the following questions. So this is the abrupt PN junction. Identify the corresponding charge configuration of the PN junction. So which of these will be the correct charge configuration for this PN junction? So correct figure is the figure A. Since it's heavily doped in the N side, the N side depletion region is much narrower, and the charges on the N side, which is ND, is greater than NA. So you have a higher, so your ND will be greater than NA, and your XN is much smaller than XP. Hence, your this is the correct figure. Identify the corresponding field profile of the at the PN junction from the figure below. So which of the four is the correct profile? That is correct. The first figure will be the correct profile. Since this is highly doped, the electric field will and has a narrower depletion region. The electric field will fall sharply in this region, and this you can get from by integrating the charge profile. So next for question 4 and 5, the doping concentration in an abrupt PN silicon PN junction at T equals to 300 K are given as Na equals to 10 power 14, Nd equals to 10 power 18. Assume Ni equals to 10 power 10, Kt by Q equals to 25 millivolts at 300 K, epsilon Si equals to 11.9, epsilon naught equals to 8.85 10 power minus 14 farad per centimeter. The built-in voltage for the PN junction is dash 2.1 volts, 1.4 volts, 0.7 volts, 3.5 volts.
Hello, sir.
Hello?
Sir, my name is Ashish Rasto.
Yes.
Sir, can you explain the previous question? How can we make the plot?
This one or this one?
Sir, that after that triangular one type.
Yes, so
Yes,
this
sir.
plot. So the electric, so we know the formula that electric field is integration of Q by epsilon Si of charge. So, so your charge is here from minus xp to 0, charge is minus qna. So integrate it and multiply it by epsilon si by q. So integrate it and divide by q. So you get it as nax. So minus nax. So when you do minus na, and you know that the electric field is zero at the edge of the electric field is zero at the edge of the depletion region. So when you put that, you will get this equation. So it will go like this, your electric field. And similarly, when you integrate over this region, you will get electric field as ndx plus ndx. So the electric field will go with a positive slope, and it will start from here and end here. So when you plot this, you will get like this. So by integrating over charge, you will get your electric field profile, and by integrating over your electric field profile, you will get your potential profile.
Okay, sir.
So for this question, The correct answer is 0.7 volts. So you just have to use the formula Kt by Q ln Na Nd by Ni square. So Kt by Q you have been given as 25 millivolts. Na is 10 per 14, Nd is 10 per 18. So it will be, and Ni is 10 per 10. So it will be 14 plus 18, 32 by 20. So that is 10 per 12. So you just have to do ln 10 per 12. And if you solve this, you will get around zero point 0.7 volts. Next question, the total depletion width of the PN junction is dash microns. 0.12 micron, 3 micron, 12 micron, 24.5 micron. The correct answer would be 3 microns. So you have to use the formula W equals to under root of 2 epsilon Si by Q, Na plus Nd by Na Nd into Vbi. All the parameters you have been given in the question. Just to put it. Vbi you have to use 0.7 volts that we have calculated in the previous question. And the answer you will get is 3 microns. Using the depletion approximation, charge configuration and field profiles are given for the PN abrupt, PN linear and PIN junctions at equilibrium conditions. Choose the correct statement. So you have been given charge profiles and field profiles and you have to match the correct profile. So first A to 1, B to 2, C to 3, A to 2, B to 1, C to 3, A to 3, B to 1, C to 2, A to 1, B to 3, C to 2. So which one is the correct match? Correct match. So the correct answer for this is C, which is A3, B1, C2. So you know for PN abrupt junctions, The electric field is linear on either side, so which is this. For p-n linear junction, the electric field is quadratic, which is this. So A3B1. And for p-n junction, the electric field is constant over the intrinsic region. So which is this? The electric field is constant in the intrinsic region. So it's A3, B1, and C2. Consider a uniform p-type bar within which a thin sheet of positive charge has been embedded. This charge is fixed at the lattice and cannot move. This forces the majority carrier holes to rearrange and satisfy Poisson's equation. Assume sheet charge density Qp in it as shown in the figure. Which of the following figures represents the electric field? That is correct. So this one represents the electric field. So this is how the charge profile will look like. It's negative in the depletion regions on either side, and there's a delta function in the middle. So when you integrate it, your charge profile will look like this. Sorry, your electric field profile will look like this. Yes, Mekara, you raise your hand. So when you embed, so this sheet of charges, it's fixed. It's not moving. But the excess carriers in this region, they can move. So what will happen is they will move, they will move to in the equilibrium due to this charges in the middle. It will create a charge gradient in this region, and to compensate for that, the charges in this region will move and create a depletion region which looks like this. So this is how your charge profile will look. So from minus xp till 0, you have a negative you have a negative charge region, negatively charged depletion region. From 0 to xp, you have a negatively charged depletion region, and in the middle you have a delta function of charges, positive, which is a positive qp. So your center will be positive qp, and so when you integrate it, so for negative, when you integrate this region, you will have your electric field as minus nax. So that will be like this, minus nax, and in this region also it will be minus nax, which will again have negative slope. But when you integrate over this delta region, you will get some very high electric field value. So that will cause electric field from jump from a negative value to a positive value, and from there it will continue to have a negative slope. So it's negative slope, then a jump to a jump, then again a negative slope. Next question. Find the magnitude of the electric field at the center of the depletion region for a silicon PN junction with Na equals to Nd equals to 10 per 15 per centimeter cube and built-in potential of 0.6 volts. Take epsilon Si equals to 12 epsilon naught. where epsilon naught is 8.85 into 10 power minus 14 farad per centimeter, 94.5 megavolt per centimeter, 94.5 kilovolt per centimeter, 9.5 megavolts per centimeter, 9.5 kilovolts per centimeter. That is correct. The correct answer will be 9.5 kilovolt per centimeter. So maximum electric field can be calculated as VBI by W depletion. And W depletion you can calculate from your built-in potential in NA and D. So when you do that, you will get your Emax equals to 9.5 kilovolt per centimeter. Consider a silicon PN junction with a uniform acceptor dopant concentration of 10 per 17 per centimeter cube on the P side and the uniform donor doping concentration of 10 per 16 per centimeter cube on the N side. No external voltage is applied to the diode. Assume Ni equals to 1.10 per 10 per centimeter cube. Epsilon Si equals to 12 into epsilon naught, which is 12 into 8.5 10 power minus 14 farad per centimeter. The magnitude of charge per unit junction area in Nc per centimeter square in the depletion region on the P side is 100, 500, 50, 20. The answer would be 50. So from the given values, you can calculate a VBI, W, and your XP, and then your answer to this question is charge equals to WP into NA. So total charge is WP into WP or XP into NA into E into A. So A is your junction area. So you have to do WP into Q. E is your electron charge 1.6 into 10 power minus 19. Na is your this given value 10 power 17. You have to calculate your XP from VBI and W. You can calculate your XP, and then you this value you when you solve it, it will come out to be 15 nano coulomb per centimeter square. A junction is made between P silicon with dopant density Na1 equals to 10 per 15% per cube. Another P silicon with dopant density Na2 equals to 10 per 17% per cube. Given Boltzmann constant K equals to 1.38 into 10 power minus 23 joules per Kelvin. Electron charge Q equals to 1.6 into 10 per minus 19 coulomb. At room temperature T equals to 300 K. The magnitude of built-in potential in volts will be 0.12, 1.2, zero point 0.8 or 2.5. So instead of a PN junction, you have a PP junction with different dopings. So I will take all the doubts in the end. So the answer to this would be 0.12. So VBI is given as KT by Q ln Na Nd by Ni square. So for the second region, you can take instead of you can take Nd equals to Ni square by Na2. So when you put or Na2 equals to Ni square by Nd2. So when you so instead of Nd2 by Ni square, you can write it as 1 by so you can write it you can replace your Na you can replace your Na by Ni square and N Nd by Ni square with Na1. So that will come here. So it will become Kt by Q ln Na2 by Na1. So which is 10 per 17 by 10 per 15. To solve this, you will get 0.12 volts. So since this is a PP junction, the built-in potential won't be much high. It will be very small. So that is all the questions I have for today. So now I will take your doubts. So in this question, so we know it's an abrupt. So since the doping is uniform, we know that it's an abrupt junction. So for an abrupt junction, the depletion region of the p side will be the charge profile will be from minus xp to 0. It's a uniform charge at qna. So the charge you have q is qna into xp, or in you can also instead of xp you can also write wp. So that is the area of the rectangle, and your and that is then so that is in one dimension, and that isn't uniformly distributed over the whole junction area. So we multiply it with the junction area, but in all our cases we consider our, our calculations to be uniform across the junction area. So we don't consider junction area in any of our calculations. We only we only do calculations in the linear in one region, in the linear region. We don't consider y and z because we are considering that everything is uniform across all y and all z. So, so what we are actually getting is Q by A. Q upon by junction area, which is our XP into QNA. So, and so Q you know 1.6 into 10 per minus 19. NA you are given in the question as 10 per 17. Only thing is you have to calculate XP. To calculate XP, what you have to do? You have to first calculate VBI from the question, from the values given in the question. You have to calculate VBI. From VBI, then you have to calculate your W, and from W, then you have to calculate your XP, and then it will be XP into QNA. So whatever value you get for XP into QNA, that is your answer. You will see the question is, consider a bar of p-type silicon that is uniformly doped to a value of Na equals to 2 into 10 per 16% mercury by T equals to 300 K. The applied electric field is 0. A light source is incident at the end of the semiconductor as shown in the figure below. The steady state concentration of excess carriers generated at x equals to 0 is delta delta P of 0 equals to delta N of 0 equals to 2 into 10 power 14 per centimeter cube. Assume the uniform, assume the following parameters: mu n equals to 1200 centimeter square per volts second, mu p equals to 400 centimeter volts per volt second, tau 1 equals to 10 power minus 6 seconds, tau p equals to 5 into 10 power minus 7 seconds, and ni equals to 10 per 10 per centimeter cube. Determine the steady state excess majority carrier concentration as a function of distance in the semiconductor. So this type of question we have done in the last class last week. So you have a generation of light at x equals to 0, and so the light is confined to x equal, generation is confined to x equals 0, and then at, so in the in the plus x region there is no generation, there is no electric field, so there is no drift current, so you only have diffusion, and so you have only have diffusion and recombination. So you only have recombination in this region, and also the and also there is no gradient in the plus x regions only, since all the excess charges are at x equals to 0. So in the plus x region there is no gradient of concentration, so diffusion is also 0. There is generation is also 0 in the plus x region, and there is no applied electric field, so drift is also 0 in the plus x region. So the only the recombination term is remaining. So so you will solve for del p by del t equals to your recombination rate, which you can calculate from your tau and mu, and when you solve this, you will get your delta. You will get your equation delta n equals to 2 into 10 power 14 e power minus x by 55.85 microns. So, so we had so in the last week we had done a similar question. So this is the same question, same as this question where you have generation at x equals to 0 and only at x equals to 0. In the plus x region there is no generation. So generation is 0. There is no applied electric field here, so your drift is 0. So you only have, and it's steady state, so your time is 0. So only the diffusion is there and your recombination is there. So the so deep your this diffusion coefficient you can calculate from the mobility you are given in the question. You can calculate depletion coefficient. You will get this equation del square delta p x by del x square equals to delta p of x by dp tau p. You solve it, you will get your equation delta p equals to a exponential minus x by lp. Similarly, for delta n, you will get exponential minus x by ln, and ln then, and this you will this value will be square root of dn tau n for delta n and dp tau p for delta p, and that is and a you will calculate this, you will calculate by boundary conditions where at infinity it's at x equal to infinity del p is 0, and at x equals to 0 del p is equals to your generation rate, which is 2 into 10 power 14. So the a would be 2 into 10 power 14, and this 55.85 micron is given as your is given by your this diffusion length, which will be square root of dn tau n. Since we are here, it's tau n, it's delta n, or for delta p it will be dp tau p. So dp and dn you will calculate from mu p and mu n. Tau p and tau n you are given in the question. So when you solve this will be the correct answer. So for so here the doping profile of a hypothetical silicon p injection is shown in the figure below. Based on the doping profile, answer the questions. So if you can solve the second question, you can solve the third question, which will just the third question is just the what is called third question is just integration over the second question. So when you are so if let's say A is the correct answer, I don't know, I have not solved this question. So for let's say if I assume that A is the correct answer and I integrate over it. So for in the this region, I have a constant charge minus q na. So when I integrate it, I will get minus q na. I will get minus nax. So this will be a linear. My it will go from linearly like this. My field will go linearly like this, and this is a linear profile. So when I integrate over it, it will be a quadratic. So it will go like this, linear and then quadratic. For this case, it will be again linear and quadratic, but it will go up and like this. For this case, it's both linear. So it will go like this and like this. For this case, it's both it will be quadratic for both regions. So it will go like this and then like this. If you have any more doubts, you can ask. A p-type semiconductor with zero electric field is under elimination in steady state condition. Excess minority carrier density is zero at x equals to plus minus 2 ln, which is this, where ln is 10 power minus 4 centimeter, which is the diffusion length of electrons. Assuming electron charge q equals to 1.6 10 power minus 19 coulomb, the profiles of the photo generation rate of carriers and the recombination rate of excess minority carriers are shown. Under these conditions, the magnitude of current density due to photo-generated electrons at plus minus 2 ln is dash ma per centimeter square. So your generation rate is constant between minus ln and plus ln at 10 per 20, and your recombination is 10 per 20 exponential minus x by ln minus mod x by ln. So it's x by ln for negative and minus x by ln for positive. So it goes like this. So you just have to put these equations in your diffusion. So you have steady state conditions. Your state. So your delta n by delta t is zero, and your the electric field is zero. So there is no drift current. So you only have diffusion current. So there you will calculate your current density from that. So you will have your dn dn del n square del square n by del x square equals to your r plus g minus r plus g or g minus r, and from there then you can calculate your current density from your that equation. You can calculate your current density, and So you have this equation. So for steady state, this is 0. Your generation rate is from minus ln to ln. Your generation rate is given as 10 power 20 per centimeter cube, and your recombination rate is given as your 10 power 10 exponential minus x by ln. So you can then multiply your, so this is 0, and then you can multiply this by whole by tau. So you have, so for this case, so you can multiply this whole by tau n. So you will have, so you have here dn tau n, which is ln square. So you will have ln square delta n by del x square minus r plus g. So your drift current will be 0, only your diffusion current will be there, and that diffusion you can calculate from your given equations here. So this is not an easy question, so it will take some time to understand and solve. So here you have given a non-uniform doping 10 per 16 minus e power minus x by L, where L is 200 microns, and you have to determine the induced electric field in the semiconductor at x equals to 100 microns. So this again is from the non. So electric field is given as minus kT by q, 1 by nd, dnd by dx. So this is basically the same question as this. So dnd, so nd of x is 10 per 16 e power minus x by L. dnd by dx will be 10 per 16 e power minus x by L into minus 1 by L. So then electric field becomes kT by q into 1 by L, and so 1 by nd cancels out with nd. So this is dnd by dx is equal to minus nd by L. So you put it here, nd cancels out, minus minus cancels out, it becomes kT by q uh, into 1 by L. So kT by q is your 26 millivolts, and uh, L is your 200 microns. So it will just be your uh, so it will be your 0.026 divided by 200 microns, which is 0.02 centimeters. So divided by 0.02 centimeters, so it comes out to be 1.3 volts per centimeter, which is given here 1.3 volts per centimeter. So you just have to use the same question as here, only your values are length and other values are changed. Please ask if you have any more doubts, otherwise you may leave. A non-degenerate n-type semiconductor has 5% neutral dopant atoms. Its Fermi level is located at 0.25 eV below the conduction band, below, and the donor energy level has a degeneracy of 2. Assuming the thermal voltage to be 20 millivolts, the difference between EC and ED is So first of all, the question here is wrong. So this is not EV, this is your ED. So this is donor energy level, not valence band. So EV is your valence band. This is donor energy level ED, which is given here, ED. First of all, that is wrong here. It should be ED instead of EV. In this case, the so if you were asking neutral dopant atoms from this case, so this case has a different meaning of neutral dopant atoms. So it means that basically, so these are the dopant atoms located at a donor energy level of ED. So, so at 0 Kelvin, all your electrons are bonded. The, all donor electrons are bonded to the donor atoms. Hence, your donor atoms are neutrally charged because they have not given any electrons yet. So that what it means by neutral dopants, that they are neutrally charged. They are not ionized yet. So this what this question says. So in this question, so this is at 0 Kelvin. All of them are neutral. None of them are ionized. Then as you increase T, there are some of them go. Some of them have. Some of them lose lose electrons, and that is called donor ionization. So the donors are getting ionized and providing electrons to the conduction band. And at certain temperature, all of, all of the donors become ionized and provide all of their excess electrons to the conduction band. So what this question basically says here is that only 95% ionization has happened. 5% dopant atoms are still neutrally charged. So only 95% ionization has happened. So your thermal voltage you have given as 20 millivolts, which is your kT by Q. So from this, first you have to calculate your temperature, and so first you have to calculate your temperature, and from that temperature, and then so if your f of E would be 0.95. So degeneracy means that each atom can contribute a so each energy state has a degeneracy means that at how many electrons, how many species are there at the same energy level and same at same energy level and same conditions. So it has a degeneracy of 2. That means it has two atoms. It has two atoms per level.